Okay, so now we're going to look at resonance structures. So resonance structures are structures that some Lewis dot structures cannot really be represented by a single Lewis dot structure. So resonance structures, all you do is you move electrons. You are not allowed to move any atoms around to do a resonance Lewis dot structure. So the actual experimental structure is actually going to be somewhat a hybrid between the contributing resonance structures. So here is a structure for a molecule. You've got a positive charge there, a neutral atom on the nitrogen. If you move that pair of electrons, and this is the curved electron pushing arrow that we tend to use a lot in organic chemistry. So you're moving that pair of electrons between the carbon and the nitrogen. You end up with a multiple bond between the carbon and the nitrogen. And now I have a positive charge on that nitrogen. So this is that molecule's resonance structure. Why is it a resonance structure? Because all we did is we moved electrons around. Electrons and charges is all we moved. We did not take this hydrogen off of here and attach it to that carbon. We did not detach from the carbon and the nitrogen and rearrange the atoms in some way. All we did is we just moved electrons and charges around. That's all we did. So this molecule is this molecule's resonance structure. The actual molecule would look something like this. It would actually have a partial double bond between the carbon and the nitrogen. You would have a partial positive charge on that carbon. You would have a partial positive charge on that nitrogen. So this is a representation of these two resonance structures blended together. So when you have a bunch of resonance structures, how do you decide which is the best resonance structure? So you want to have as many octets as possible in your best resonance structure. You want to have as many bonds as possible in your best resonance structure. You would like to have, if there is any kind of charge on there, you would like to have the negative charge on the most electronegative atom. If there is a positive charge, you want to have the positive charge on the most electropositive atom. You want to have as little charge separation as possible, so that gives you the best resonance structure. So if you have more than one resonance structure and you're asked to choose the best one, this is what you would use to decide. So major contributor to a resonance structure is the one that has all of an octet around every atom. So for instance, you got this structure and you got this structure. We'll often use this as an intermediate in a reaction mechanism in organic reactions. But here's the structure of formaldehyde, and here is the Lewis dot structure, resonance structure for this molecule. So what I did is I took this pair of electrons, I moved them up there using my little curved arrow. So now I have a positive charge on that carbon and I have a negative charge on that oxygen. Carbon does not have an octet. Oxygen has an octet. So in this structure of formaldehyde, all of the atoms have an octet. You have more bonds here. You only have 3 bonds here. I actually have 4 bonds here. There is no charge separation. This actually doesn't even have any kind of charge. This has a charge, and you actually have a charge separation. So this is not as good a resonance structure as this structure. So this is a bad resonance structure. This is a good resonance structure. But they are both resonance structures. And this does have a minor contribution to the entire structure. So if you wrote out this molecule and you were asked to write out the dipole moment for this, you could actually do this just from the electron negativities, not necessarily having to do the resonance structure. But carbon is less electronegative, oxygen is more electronegative, so the oxygen gets the partial negative charge, the carbon gets the partial positive charge. And here's the dipole moment arrow with the positive sign of the dipole moment arrow, where you have the partial positive charge. Or you could have gotten this from looking at the electronegativities of the atoms, from remembering that oxygen is close to fluorine, carbon is far away from fluorine. You could have decided it that way, or you could look at this resonance structure and you could see that this has a positive charge and a negative charge, and you could have given it a partial positive and negative charge as shown here. So here is acetic acid. If you do a reaction of acetic acid, the hydrogen drops off and you end up with this structure. So this is when acetic acid acts as an acid and loses its H+, and then you end up with this. So when you have something that looks like this, you can actually do a resonance structure where you move the pair of electrons around. So this electron pushing arrow is going to take that pair of electrons and put it between the carbon and the oxygen. It's going to take this pair of electrons between this carbon and the oxygen and move it out to become a lone electron on the oxygen. So this is this molecule's resonance structure. And you can actually see by looking at this that these actually are very symmetrical. So if you rotated that this bond around, then you would end up with something that looks like this. But this is the acetate ion resonance structure. So in this case, you have the negative charge delocalized over both atoms instead of it being just on one of the atoms. So instead of each oxygen atom getting all of the negative charge, it sort of distributed it. So that's why an acetate ion is actually fairly stable, because you have delocalized charge. Also, if you can write out more resonance structure for a molecule, it will be more stable because it stabilizes the molecule if you can write out more resonance structures. So in this case, each of the carbon-oxygen bond is halfway between a single and a double bond. So these are all 1.5 or bond order 1.5 or 1.5 for each of the carbon-oxygen bonds, because it has half of a bond between the two sets of oxygens. So now we're going to talk about writing chemical formulas. So you got Lewis dot structures and you have the condensed structure. So this is a Lewis dot structure where you show a line for each pair of electrons, and here's the condensed structure. So most of the time the condensed structure and the skeletal structures are ways that organic chemists can write complicated molecules without doing a lot of writing. So all you did there is you took this molecule and this carbon that has 3 hydrogens attached to it, I wrote it as CH3 instead of actually writing out all of the hydrogens. And here you got a carbon that's attached to 3 hydrogens, so I wrote it as CH3. So this is a lot easier to write on a straight line than to actually have to draw out the Lewis dot structure. So condensed formulas are written without showing all of the individual bonds. So you're not actually showing the bonds individually, you just show it as the condensed structure. So here's my carbon 1, here's my carbon 2, and then you have the things that are attached to it. So when you write this, you usually write it like this. You write it as CH3CH3. You usually do not write it as H3CCH3, although, you know, if you're drawing something that's a hybrid of a Lewis dot structure and a condensed structure, you may sort of end up doing this just to make it clear where the hydrogens are attached. Okay, the other thing is when you're writing molecules that have more than one same thing, so you've got like 3 CH3s attached to the same carbon, instead of writing out the 3 CH3s individually, you can actually put a parenthesis around it and then just put a subscript to tell how many of those you have. So that's another way that you can make this even a simpler structure than given here. Although in this case, this is really the only way that you can write that molecule. So here are some Lewis dot structures, and here's the condensed structure form of that molecule. So when you're given a condensed structure, you sort of have to look very carefully and try to figure out what it means. So in this molecule, I have CH3, CH, another CH, and then I have CH3. So I can write it like this, or I could write it with the double bond shown like this. So either of these are okay for condensed structural formulas. Here's another molecule, so I got a triple bond between the carbon and the nitrogen. I've got a carbon to which I have 3 hydrogens attached, so I can write CH3CN, or I can actually show the triple bond. Here is CH3, and then CH, and then O, so I can write it like this, or I can actually write it sort of like a hybrid between a condensed structure and a low-stat structure, actually showing the double bond between the carbon and the oxygen as shown here. So here is CH3 carbon, and then you can write the oxygen beside it, and then the CH3 like this. Or if you want to show a little bit more detail, you can show CH3 carbon double bonded to that oxygen, and then the other CH3. Here's my acetic acid. I can write it as CH3CO2H like that, or you can actually show the double bond like that. Or if you don't want to bother doing that, instead of writing out the two oxygens right next to each other, you can just write O2 like that. So any of these are perfectly valid condensed structural formulas. So what do I normally do? So what I would do is I can give you a condensed structure and ask you to come up with a Lewis-Stat structure from it. I can give you a Lewis-Stat structure and ask you to come up with a condensed structure from it. So that's like a common question that I tend to ask on my quizzes. So what's a line angle drawing? Well, if you're too lazy to even write out the condensed structure, oh, who's got time to write all those subscripts? You can do this. Here's my line angle drawing. So this is the same thing as that. And see how this is so much easier to draw. I mean, if you just had a piece of paper and you were writing things, this would be very easy to draw. It might be a little hard to write, to type up on a piece of paper, but this is easy to draw. So this means this. So this is a line angle drawing. Sometimes it's called a skeletal structure. Sometimes it's called a stick figure. I like skeletal structure for the name for that. Okay, so what you do is you represent each bond by lines, and every time you bend the line, there is a carbon. So there's a carbon here, there's a carbon here, there's a carbon here, there's a carbon here. So whenever the line bends, there is a carbon. You don't actually show the hydrogens, because if you show the hydrogens, it's just the same as doing a Lewis-Stat structure. So we don't have to draw in the hydrogens. The hydrogens are all left off. So this is the same as that. So here's carbon, 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 carbon. This carbon would have 3 hydrogens attached to it. This carbon would have 2 hydrogens attached to it. This carbon would have 2 hydrogens attached to it. This carbon would have 3 hydrogens attached to it, but I don't draw them in. If you have nitrogens, oxygens, or halides, or some other heteroatom, so atoms other than carbons and hydrogens, you actually have to show them. Because if you leave them out, then everybody will think that it's actually either a carbon or a hydrogen. So here is the representation of this molecule written out as a skeletal structure. So here's my bond 1. Okay. So between 1 and 2, there's that bond. Between 2 and 3, there's that bond. Between 3 and 4, there is that bond. Between 4 and 5, there is that bond. Between 5 and 6, there is that bond. Now, when you have a multiple bond, you have to show them, and then you have to show the heteroatom. Do you have to have the hydrogen there? You can leave it out. If you leave it out, it means the same thing. Atoms other than carbon must be shown. Double and triple bonds must also be shown. Okay, so what we were doing in our previous slide, so if the way I tend to ask questions about that kind of stuff is I will give you the line bond structure and ask you to come up with the Lewis-Stat structure, or I'll give you the Lewis-Stat structure and ask you for the angle structure, or I'll give you a condensed structure and ask you for the line angle structure, and so on. So variations thereof. Okay, so now we're looking at wave properties of electrons. Now, because electrons have the duality of being both a wave and a particle, you can actually represent electrons as a math function that describes a wave. So when you have a wave function, psi, this is a mathematical description of the size, shape, and orientation of that wave function. The amplitude can be 0, it can be negative, and a node is when the amplitude is 0. So this is the way that most people draw a p orbital. So here's my atom, and here is my p atomic orbital. The p atomic orbital has a positively signed part, and it has a negatively signed part. If you draw it as a wave function, this is what it would look like. So you've got a negatively signed part of the p orbital. You got a positively signed part of the p orbital, and this is where electrons are likely to show up, either at the positive lobe or the negative lobe. So electrons are showing up here. This is known as a nodal plane. So the nodal plane at 0, not positive, not negative, just at 0. That means that there is zero possibility that the electron is located here. So the electron would be here, electron would be here, but it would not be in the middle because it has a nodal plane there. So the electron has zero possibility of being at the nodal plane. So here's my nodal plane. The electron is not there. And then you don't have to have the negative end and the positive. Nobody memorizes which side has the negative and which has the positive. You could also represent it like this, where you have the positive lobe here and the negative lobe here. And you often will actually have this interconverting when you actually have an actual molecule. So you have a nodal plane here, nucleus, positive sign, positive lobe, negative lobe, negative lobe. But when you're trying to do bonds between two atoms, what you have to do is the sign of the lobe actually has to match. Otherwise, it does not work. A sigma bond is between the two nuclei. So you can form a sigma bond between two s orbitals. You can form a sigma bond between two p orbitals. You can form a bond between an s and a p orbital. You can also form a sigma bond between hybridized orbitals. So when you have a sigma bond, the bonding molecular orbital is lower in energy than the original atomic orbitals. So here is the representation of sigma bonding molecular orbital. So you have two atoms that have their individual orbitals. So here's my s orbital, here's my s orbital. You combine them together and you get a bonding orbital. So now you actually have a significant portion of the electron density between the two atoms. So this is my bonding orbital. You can represent it like this. So you got a positive lobe, you combine them together and you end up with a sigma bond that also has positive lobe. So this is my sigma bonding molecular orbital between two 1s orbitals. And let's say this is a hydrogen atom that has an s orbital and another hydrogen atom that has an s orbital. And they form the bond and we end up with a sigma bonding molecular orbital like this.